Hello everyone, my name is ZHEN and today I'm going to explain topic 2, Deadlock. Before we dive into the tables, let's imagine a real-life scenario. A bank has a limited amount of money. Customer can borrow money, but the banker must always check, if I lend more, will I still have enough for others later? If the banker is careless, some customer may never get the money and the whole system will freeze. This situation is exactly what we call a deadlock. In operating systems, where processors are like customers, stuck waiting for each other forever. So the banker algorithm works just like a careful banker. It checks every request to make sure the system stays safe and avoid deadlock. Now, let's look at this table. So we have 5 processors from P0 to P4 and 3 resource types, which is A, B, and C. For each process, we can see 2 things. The first one is allocation, which is that what the processor is holding right now, and think of this as money already borrowed from the bank. And the second one is max, which is the maximum amount the process may ask for. This is like the customer credit limit. So why do we care about these numbers? Because they allow us to answer 2 key questions. The first question is, can the system still operate safely with the current allocations? And the second question is, if we grant more resources, will we risk a deadlock? Let's look at the question. According to the question, we need to draw a resource allocation graph. And for this graph, we have 4 parts we need to remember, which is processors, resources, instances, and allocation. We use circle to represent the processors, square for the resources, which is A, B, and C, and the dot inside the square used for represent the instances. So number of instances we can get from the questions. And an arrow from a resource to a process means the process is holding that resource. For example, P0 has 3 units of A and 2 units of C. You can think of this as counting how much money P0 currently holds. So in the graph, we allocate 3 dots from resource A and 2 dots from resource C to P0. The next part is also same. We look at the P1. It only has 2 units from resource A. And P2 only have 1 unit from resource B. P3 have 3 units from A, 6 units from B, and 3 units from C. And the P4 has only 2 units from C. So here is our resource allocation graph. Now we can draw the available table. Remember that in the graph, each dot of a resource node represents 1 instance. Some of these instances are already connected to a process through allocation edge, and the rest are still free. The free ones are exactly that we call available. So instead of just looking at the number in the table, we can actually count the remaining dots in the graph to find available. For example, for resource A, we can see that 4 instances are still free, for B is 10, and for C is 9. So our available table is 4, 10, and 9. This factor is very important because it tells us starting the point of the safety algorithm. In other words, these are the resources can immediately give out without any risk. Let's start to next question. Use the safety algorithm to determine whether the system is in a safe state. First, we need to prepare a needs table. How to know the needs of processors? We can use the max to minus the allocation. Like for the P0, we use 9 to minus 3 to get 6, 0 minus 0 to get 0, 2 minus 2 to get 0. And the next one is also same. 5 minus 0 to get 5, 6 minus 0 to get 6, 2 minus 2 to get 0. 3 minus 0 to get 3, 5 minus 1 to get 4, 7 minus 0 to get 7. 5 minus 3 to get 2, 6 minus 6 to get 0, 5 minus 3 to get 2. And the last one is P4. We use the 3 minus 2 to get 1. 3 minus 0 and 4 minus 0, we get 3 and 4. After we finish the need table, we can start to run the safety algorithm to check if the system is in a safe state. The rule is very simple. We need to check whether the need is less than or equal to the available and is true. If the need is greater than or equal to the available, which is false. Let's go step by step. P0 needs 600, but available is only 4, 10, 9. 6 is smaller than 4. This is false and P0 cannot run now. That means we need to skip the P0 and go to the P1. For the P1, we need 0, 6, 5 and the available is 4, 10, 9. So that means it's true. If the P1 is true, we need to add the allocation. The allocation is 200. We need to add the 200 in the available. 4 add 2 is 6. 10 add 0 is 10. 9 add 0 is 9. And the next one is P2. P2 needs 7, 4, 3. And its available is, look at here, which is 6, 10, and 9. So it's false. It cannot run. We need to look at P3. P3 needs 2, 0, 2. And the available is 6, 10, 9. This is true, so P3 can finish. It releases 3, 6, 3, and available become 9, 16, and 12. Now look at P4. It needs 4, 3, 1, which is less than 9, 16, 12. So this is true. So P4 can finish and it will release 0, 0, 2 and making available 9, 16, and 14. Because we have two false processors cannot run, we cannot just leave it. We need to use it again, like P0. And the latest available is 9, 16, and 14. We need to compare the needs of the P0 to the latest available. So 600 is less than the 9, 16, and 14. So that means this is true and P0 can finish and release 302. Available will become 12, 16, and 16. And finally, P2 needs 7, 4, 3, which is less than 12, 16, 16. So the final available is 12, 17, and 16. Since all processors can finish one by one, that means the system is in a safe state. So our conclusion is, the system is in a safe state and the safe sequence is P1, P3, P4, P0, and P2.
Thank you for LING, and I'm Ong Po Ling. I will start with the section C, which is, suppose now P3 requests additional instance 039. Can it be granted using the banker's algorithm? So now we need to start with the resource request algorithm to check either the process 3 can be granted or not. Step 1. We have to check our request for P3. Is it less than or equal to P3 needs? The P3 request for now is 039, and based on what we have, P3 needs is 202. So let us check one by one. The 2 is more than 0, so it is correct, and 3 is more than 0, so it is false. Actually, when it is false, you no need to proceed to update the banker's algorithm, and you no need to check the safety algorithm anymore because it is false. So we can just only go through with the conclusion. We can write on this way, which is no, the P3 request cannot be granted because it exceeds the P3 needs. So let us continue with the question D. Based on question C, can request 100 from P2 be granted? And we have to provide our reason. Let's start with the resource request algorithm. Step 1, we have to check our request for P2. Is it less than or equal to P2 needs? And now our P2 request is 100 and our needs is 743. So 7 is more than 1 and 4 is more than 0, 3 is more than 0. So this condition will be true. And let us continue with step 2. So now we have to check on our request for P2. Is it less than or equal to our available just now? For now, P2 is 100 and our available is 202. 202. And 2 is more than 1, 0 is equal to 0, 2 is more than 0. So this condition will be true also. So we can start with our banker's algorithm. Both of our conditions are met. We need to update 3 tables for banker's algorithm. The first table, which is allocation table, we have to finding our new allocation for P2. Just take our old allocation, which is 0, 1, 0, and I'll add with our new request, which is 100, and we will get our new allocation, which is 1, 1, 0. And here is our new allocation table. All of the value, we take it from the allocation, earliest allocation, and we just update for the P2 to our new allocation. So now the second table that we have to update, which is available table. How to find our new available? We have to take it back our old available, which is 4, 10, and 9, minus with our request, which is 100. So we will get the 3, 10, 9, and this is our new available. And here is the available table. And the next table, which is the last table, the needs table that we have to update. For finding the new needs, we have to take it back our old needs, which is 7, 4, 3, minus with our request, which is 100, and we will get the value, which is 643. Or you can either use another methods to find our needs, which is our needs formula. You can take the max minus the new allocation. The previously max is 753, and minus with our new allocation, which is just now we counted 110, 643 is same value with the formula previously. And now we can go through with our safety algorithm. So first we have to check the program needs. Is it less than or equal to our available? So let us begin with our P0. P0 needs, which is 600, is it less than or equal to 3, 10, 9, which is our available? So 3 is not more than 6, so it will be false. So when a program is false, we will keep trying to another process in the list. So you have to make sure that we check every single resources type, like when it is all fulfilled, and then only we can say true. So next, let us proceed to check for P1. P1 needs, which is 065. Is it less than or equal to 3, 10, 9, which is our available? So let us check one by one. 3 is more than 0, and 10 is more than 6, 9 is more than 5, so it will be true. When it is true, we have to update our available, because right now we will set that this process we have enough of resources for its run. Okay, for example, like this person, he want to borrow 100 ringgit, and you got this amount, and then you will say that, yeah, I have this amount, I will lend it to you, I will borrow you. And then after this, the person will give it back whatever that you given previously. So according to allocation for P1, we have to allocate 200. So whenever process finish executions, it will return this allocated resources to the system. So we have to update the available. 3 plus 2, we got 5, and 10 plus 0, we have 10. 9 plus 0, we got 9, and we will go through with P2. Let us check 6, 4, 3. Is it less than or equal to 5, 10, 9? So 5 is not more than 6, so it will be false. So next, P3. 2, 0, 2. Is it less than or equal to 5, 10, 9? So 5 is more than 2, 10 is more than 0, and 9 is more than 2. So we can look back to our earliest allocation, which is 3, and now we can look through for our previous allocation for P3, which is 363. So 5 plus 3, we got 8, 10 plus 6, we got 16, 9 plus 3, we got 12. And next for P4, 4, 3, 1, is it less than or equal to 8, 16, 12? So 8 is more than 4, 16 is more than 3, 12 and 12 is more than 1. So for the previous allocation for P4 is 0, 0, 2, and 8 plus 0 is 8, 16 plus 0 we got 16, 12 plus 2 we got 14. And next, the P0, 600, is it less than or equal to 8, 16, 14? So 8 is more than 6, 16 is more than 0, and 14 is also more than 0, so it will be true. Our previous allocation, which is 302, so add it back. 8 plus 3, 11, 16 plus 0, 16, and 14 plus 2, 16. So continue with our P2, 643. Is it less than or equal to 11, 16, 16? So 11 is more than 6, 16 is more than 4, 16 is also more than 3. So it will be true. Our previous allocation for P2, which is 110. So add it up. 11 plus 1, 12, 16 plus 1, 17, 16 plus 0, 16. So now we can go through with our conclusion. For conclusion, we have to list up our safe sequence first. How to find our safe sequence? Actually, the safe sequence is based on the first process that we get through. So the first process is process 1, and the second process 3. The third one is P4, and the continue is P0, and the last one is P2. So the conclusion we can write like this way. The request 100 from P2 can be granted as the system is in the safe state and deadlock can be avoided. So that's all for my presentation. Is there any question?
Yes, I have one question.
Yes.
What happens if the safe sequence cannot be found?
If you are unable to find your safe sequence, then you will conclude that the system is not in the safe state and there is a possible for deadlock occur.
Understand. I also got question. In
Yes.
safety algorithm, why we have to always update our available while the condition is true?
Because that we have to always update our available. We will say that this process have enough of resources for it run. So when the process is start already, it will assume that the process will run until finish. And when it is finished, the process will return the resources back to the system. So the remaining resources will increase. So you have to update your old location to our new available. That's it.
Okay, thank you. What if a process asks for more than its declared max?
The banker will immediately reject the request as unsafe and log an error.
Thank you. Why do we release resources back to available after a process finish?
So the other processors can borrow them and keeping the system moving and preventing a standstill. Do you have any other questions?
No more. Thank
Okay.
you.
Thank you.